In this second video for Chapter 3, we're going to look at another model that will help us determine temperatures in situations where we have heating and cooling going on. So we'll work for a situation when we, say, bring a cold liquid into a warm room, or we'll also work for a situation where we have a room surrounded by an outside temperature, and we want to know what the temperature in the room will do as the temperature outside changes. So the model that we're working with looks like this. And so let's tag everything. Capital T of T is temperature, or let's call it inside temperature, or the temperature of the object. M of T will be our outside temperature. This K out front, this constant, will be either something that we will be given, which is constant based on the characteristics of the building, how much insulation it has, or it would be a constant that we would be determined if we are, say, bringing a cold liquid into a warm room and we have some data to determine that. dt out front here would be change in temperature with respect to change in time. And then these two quantities at the end here, H for heating rate and U for cooling rate, in all the cases, all the problems that we will do, we will assume that those two rates are zero. So if we take this model and write it into a better form by taking this T of T term and moving it to the left side, then our model looks like this. And we see that this is then a linear differential equation. This constant right here becomes our P of T, and all of this right-hand side here becomes our Q of T. And so since this is a linear differential equation with an easy constant P of T, let's go to the next blackboard to determine its solution. So mu of T would be e to the integral of k dt, which would be e to the kt. And so back here we're solving this differential equation for capital T, the temperature. So capital T would be 1 over mu of T, which would be e to the minus kt, integral of q of T, mu of T, which is e to the kt, dt plus c. And so there is our model for temperature at time t. So let's work two examples here. Case 1 would be where we are going to let m equal m0. M is the outside temperature, but we're going to say the outside temperature is a constant. And then remember that Q of T was K M of T plus H of T plus mu of T. We're saying that the heating is 0 or cooling is 0 to make our model easier, and that m is m0, so Q of T is k m0, and so if we set up this integral above, here's what we get. And so this is easy to integrate. What is in the brackets becomes what? K m0 times e to the kt over k, and that is just plus c. And so what's in the brackets becomes just that would be just what? m0 plus or m0 e to the kt plus c. And so when we combine, or when we do this distributing of e to the minus kt across the brackets, here's what we get for T of T. So T of T equals m0 plus e to the minus kt. T of t equals m0 plus c e to the minus kt. So on the next blackboard, if we pick that up and find the constant c, and remember that m0 was our outside temperature, or in some cases we would call it our surrounding temperature in the case that we're bringing a cold liquid into a room, then m0 would be the room temperature. And so if we assume that T of 0 is T sub 0, the temperature at time 0, we just write that as T sub 0, then we get T0 equals M0 plus C e to the 0, or C equals T0 minus M0, or you can take this differential, this solution, and write it in this form, that T of t is m0, replace the c with T0 minus m0, the initial temperature minus the outside temperature is T0 minus m0, e to the kt. So this is our case 1 formula where we have a constant outside temperature or a constant surrounding temperature. So the formula for temperature of our object is pretty simple. M0 is known, T0 is known, and we just we do need to find that constant K. So the way a problem like this would typically work would be we would have the temperature of an object at 2 different times, and that would allow us to find K, and then we'd find the formula. So let's work an example of this type on the next blackboard. So filling in the information, the M0 is the surrounding temperature, which is 7 degrees. The T0 is the initial temperature of the beer, which is 35. M0 again is 70. And so our T of t formula is this. To find the constant K, we plug in the known information that T of 3, the temperature at 3 minutes, or after 3 minutes, is 40 degrees, and that would equal what? 70 minus 35 e to the k times 3, because T is 3. So let's pick that up on the next blackboard. 40 equals 70 minus 35 e to the 3k. If we move, rearrange, 35 e to the 3k equals 30. E to the 3k equals 30 over 35, which is 6 over 7. Take the ln on both sides. 3k equals ln of 6/7. Actually, let's do that differently. Let's say that e to the 3k is 6/7, so e to the k to the third, right? Because a to the mn is a to the m to the n. So e to the k to the third is 6/7, and taking cube roots of both sides, we get e to the k is 6/7 to the 1/3 power. And so remember that our differential equation, or our general form, was T of t equaled what? 40, equal T of t was 70 minus 35 e to the kt, or e to the k to the t. So if we rewrite that, we get T of t equals 70 minus 35 e to the k is 6/7 to the 1/3. So that's 6/7 to the 1/3 of the t, or 6/7 to the t over 3 is our solution, and that's the temperature of the beer at any time t. And then the final part of the problem is to find the temperature at 20 minutes, so T of 20 would be 70 minus 35, 6/7 to the 20 over 3, and you can put that in your calculator to see that you get about 57.5 degrees is what the beer will warm up to after 20 minutes. So there's an example of this simpler of the two models, this one right here, and now let's take a look at the other case when the temperature outside is not constant. So here is our model. In this case, we said we're going to assume that the outside temperature m of t is not constant. We're going to assume that m of t is a sine wave and that it looks like this. B0 minus b cosine omega t. We'll put up a graph of that in a minute, and that both the h of t, the cooling rate, or the heating rate and the cooling rate are 0. So let's graph our m of t. The B0 would be the average outside temperature, and so let's put B0 right here. Let's make this B0 minus this other constant here, B, this constant here, and let's make this B0 average outside plus B. So at time 0, given that this is a cosine function, cosine of 0 is 1. So it becomes B0 minus B times 1, so our initial temperature is right here. 12 hours later, if we assume that the omega is 2 pi over 24, or pi over 12, then omega times 12 is going to be pi, right? And so cosine of pi is minus 1. So m of t is going to be m of pi is going to be b0 minus b times minus 1, which is b0 plus b, which is up here. And then finally, if we put in m of 24, m of 24 hours. Actually, I think I wrote something wrong previously. The first thing that we just did there was m of 12, which is the same as plugging in pi, and that was b0 plus b, and m of 24 is going to be 24 times omega, so that's m of 20. So m of 12 became b0 plus b. M of 24 is m of pi over 12 times 24, m of 2 pi, which is b0 minus b. So we're back where we started with at 24 hours. So the outside temperature graph looks like this. So it's a sine function or a cosine function, but we're taking a portion of it that's not the typical way we look at a sine function. So what does this t of t function turn into in that case? So let's set that up on the next blackboard. So remember that we're replacing the q of t with k times b minus, or b0 minus b cosine omega t, that outside temperature function. So let's split that into two integrals. So the first part would just be KB0 e to the, or integral of e to the kt, just a constant outside, bring the constant outside. And then minus kb will bring that constant outside, but now we're integrating cosine omega t e to the kt dt, and then finally there's a plus c under there. So the first integral is easy to do. It is just going to be so leave the kb0 here, integrate e to the kt, and we get e to the kt over k. And then this integral, everything else we have to leave alone, the same. So all of this part right here, after cancellation, e to the minus kt times e to the kt, e to 0, the k's are going to cancel out. And so that first term is just going to be b0. And then we have all this, and here's the term where we have to put all the work into it, this integral right here. So that integral is an integral of a special type. If you look on the front flap of your book, you see this formula. So let's replace the integral with that. So the b0 stays the same, minus e to the minus kt, and that is multiplied by, according to our formula, e to the kt k cosine omega t plus omega sine omega t, all divided by k squared plus omega squared. And then the last term does not change, this c e to the minus kt, but we're going to assume that enough time has passed that this decaying exponential goes to 0. So let's look at what we have here, and notice that this part right here is just 1, and so here's what we get. I had forgotten to carry forward the KB here and here, so when we combine all this together, here's what we get. Alright, because the e, the minus kt times e to the kt, when we multiply that together we get 1, so we bring the minus kb forward, and we bring all of this part right here forward, and we get this. So now let's bring this k across, so we get t of t equals b0 minus b, and then what, k squared cosine omega t plus omega k sine omega t, right, because we're bringing this k across here and here, and we get this. So now let's multiply by 1 over k squared times 1 over k squared, and that gives us t of t equals b0 minus b times cosine omega t plus omega over k sine omega t divided by 1 plus omega over k quantity squared. So that's our formula, and so let's explain a little bit about it. We're going to actually want to move it into an alternate form, but let's see what we've got at this point. So the B0, remember, is the average outside, and so the B0 is the average outside temperature. This B in front of this bracketed expression is the swing temperature, and then we're going to have to look at this bracket expression another way because it's too hard to make sense of in the current form. So let's go back to our graph of the outside temperature. So B0 is the average outside temperature right here, and then we're subtracting B or adding B, and so we're either moving from the average down to B0 minus B, or moving from the average to B0 plus B, so that's why we're calling that B the swing temperature. So turns out that we can rewrite T of T, or rewrite this expression right here in a different way. So let's see how that can also be written. So we're able to write this bracketed expression on this line as this, and when we write it that way, it's just a variant, as it turns out, of the initial outside temperature, which you remember was what? B0 minus B cosine omega t. So we're going to graph both outside temperature and inside temperature together on the next blackboard. Let's take a look at these parts of this formula. This factor right here we're going to call a scaling factor. It tells us how much, what portion of the outside temperature carries over. And then if we take this portion right here and take the omega t minus phi and set it equal to 0, we get t equals phi over omega, and that tells us how much there is a time shift. The scaling is usually a constant between about 0.7 to 0.9, sometimes higher, sometimes a little lower, depending on insulation. So we're here talking about a building, and it's how the outside temperature affects the inside temperature. The time shift is typically between 1.5 to 4 hours, and so if you have great insulation, you'll have 4 hours or more before the outside temperature affects the inside temperature. So let's look at a graph of this on the next page, next blackboard. In blue here we have the outside temperature graph. Now let's plot the inside temperature graph in a hypothetical situation. So we've added the inside temperature graph in purple. So notice that the low temperature inside does not get as low as the low temperature outside, and the low temperature, or the high temperature inside, does not get as high as the high temperature outside. And also notice that there is this time shift, right? When the low temperature is reached, inside is, looks like by this graph, maybe 3 hours later. When the high temperature is reached, it's also later, and when we get back to the low temperature, that's also later. So here we see it in graphical form. Now let's do it, calculate everything with an example like problem number 8 in the text. So the time constant is given as 2 hours, and k is defined as 1 over the time constant. So k is 1/2. That's this k in the formula that shows up in a variety of places, right? This k here, and we're given that the minimum temperature is 50 degrees, and the maximum temperature is 80 degrees, and so the average outside temperature would be the min plus the max divided by 2, 130 divided by 2, which would be 60, The swing temperature would be either the difference between that average temperature and the low, or the difference between the high and the average, and so the swing temperature is 15 degrees, and that's in our hypothetical chart. The swing temperature is that much, right? That much there, and that much in between the lows. I'm sorry, that's not right. The swing temperature is the difference between the average and the low, or the difference between the average and the high. And so in our case, that is 15 degrees in our example here. So we've got that. Now we also, in our formula, need to know the scaling factor. So the scaling factor is 1 over the square root of 1 plus omega over k quantity squared, and we know that omega is always defined as pi over 12. In our case, k is a half, so omega over k is pi over 6, so the scaling factor will be 1 over the square root of 1 plus pi over 6 quantity squared, and that turns out to be about 0.886. And then what about the time shift? The time shift is t equals phi over omega. Phi is defined as the tangent of omega over k, which, or tangent inverse of omega over k. Tangent of phi is omega over k, and so that would be the tangent inverse of pi over 12 over a half, or the tangent inverse of pi over 6, and so that you can see from your calculator is about 0.412 is phi, and so t is 0.412 times omega, or divided by omega, divided by pi over 12, which is 0.412 times 12 over pi. And so if you do those calculations, you see that that is about 1.8 hours. So if we started off at 2 a.m. was the low and 2 p.m. was the high, we see that the low inside and the high inside would be 1.8 hours later, which is about 3:51, or actually closer to 3:52 a.m. and p.m. And then the outside temperature low was 50, which was 65 minus 15 was the low, and that was outside. What about inside? It's going to be 65 minus 15 times that scaling factor, which was 0.886, and that number is about 57.5 degrees, so it doesn't get quite as low inside. And the high was the average temperature plus the swing temperature of 15, but inside that would be 65 plus 15 times 0.886, and that number is about 78.3. So it doesn't get as low and it doesn't get as high. I had a mistake there. This low is 51.7 and the high is 78.3. So it almost gets as low inside as outside, and it almost gets as high inside. That's because the insulation is not that good with a time constant of 2 hours. But we'll see in later problems when we have a time constant of 4 hours or 5 hours, then we can get a outside versus inside temperature difference of maybe 8 or 9 degrees as opposed to just a couple of degrees. And so there we have that problem. You might want to stop the video now. I'm going to, in this final part of the video, show how we how do we go between this version of the formula, which turns out to be unwieldy because we can't work with it, to this version of the formula where we change the f of t, the bracketed expression here, to a form where it looks very much like the outside temperature. So let's take a look on the last couple of blackboards how we do that. It's just trigonometry that we're doing. So converting from one formula to the other, we start with the tangent of phi, or the relationship between phi, omega, and k having to be, to make this conversion, that tangent phi equals omega over k. We set up a triangle. Tangent is opposite over adjacent, so there's omega, there's k, and then the hypotenuse would be what? Omega squared plus k squared. And then if we use the trig formula, that cosine A minus B is what? Cosine A, cosine B, plus sine A, sine B. And so what does that give us? That, so back to the triangle, the cosine of phi would be the adjacent over the hypotenuse, which would be this, and the sine of phi would be the same, almost the same thing, but with omega in the numerator, right? And so if we expand this using this formula, we're going to get cosine omega t, and then cosine of phi is going to be times k over square root of omega squared plus k squared, and then plus sine omega t sine phi, so that's sine omega t, and then sine phi would be, as we said, or as we showed, omega over square root of k squared plus omega squared. So you can see how it's shaping up now to look like the other form. If we distribute, all right, let's just do one more rewrite. This 1 over 1 plus omega over k squared, if we do a little bit of algebra, so if we look at this algebra up here in the corner, get a common denominator in that radical, and it becomes then this out front, so it's 1 over square root of k squared plus omega squared divided by k, but that's the same as k in this numerator, so we're going to distribute that across, and then let's put what? Let's change the order here. K over omega squared plus k squared cosine omega t plus omega over k square root of omega squared plus k squared over times sine omega t. So you can see that these expressions here, or these factors here, when we distribute, are going to get rid of the square root in the denominator, so it looks like this on the next blackboard. Like this, we're just distributing across here, and then if we take the numerator and denominator and multiply by 1 over k squared by 1 in that form, we get what? Cosine omega t, because the k squared out front is gone, and then omega over k divided by k squared is omega over k times sine omega t, and then both denominators are divided by k squared, so the k squared over k squared is 1, and then the omega squared over k squared, or divided by k squared, becomes this. And so we've converted from we've converted from this form to this form. Of course, what we and we could go back the same way. Of course, the form we want to use is this form here. So that just shows us how we convert to this other form. So one more look at the graph and the calculations we did on that example problem. So here's the graph in blue of the outside temperature, and in purple of the inside temperature. The time constant was given to be 2, so the constant k in the problem is 1/2. The 1 over the square root of 1 plus omega squared scaling factor, which is 1 over square root of 1 plus pi over 6 squared, is 0.886, which means which is actually showing there's not very good insulation because it's close to 1. And the outside temperature average was 65, which was what, 50 plus 80 divided by 2, so we calculated that. And then the swing temperature, it went from 65 to 80 and down from 65 to 50, so the swing temperature was 15. And then we wanted to use the formula, so we calculated the time shift, which is phi over omega, given that phi is tan inverse of pi over 6, and that turned out to be 1.8 hours, which changed our low and high inside and outside from 2 a.m., 2 p.m. to 3:52, and then the low inside was this 50 degrees, and the low outside was 80 degrees, but with the scaling factor of 0.886, we only drop it 15 degrees times 0.886, so the low inside is only 51.7, doesn't go all the way down to 50, and the high inside, we add 15 times the 0.886 to the 65, so it doesn't go all the way, quite all the way up to 80. It only goes to 78.3. So these determinations of the of the low and the high inside and outside are just done by multiplying the swing temperature by the scaling factor. Swing temperature by the scaling factor, and either adding or subtracting to the average temperature, and the calculation of the time shift, phi over omega, is first done by calculating phi, tan inverse of omega over k, dividing that by omega, which is pi over 12, and here we got the time shift of 1.8 hours. So our formula here is pretty pretty messy looking, but it's easy to determine this scaling factor, and it's easy to determine the time shift, and so we don't really have to work fully with this formula. We just work with certain parts of it, and it makes these problems relatively, or certainly easier to do than it looks like by the complexity of this formula and the derivation of this formula. So this concludes this video on section 3.3 of your textbook, Heating and Cooling of Buildings.